on the YouTube side of this kind of thing. Remember seeing what they used to connect to.
Well, I have to actually shut down the audio so we don't get a bounce. All right. Well, thanks everybody for being patient. Welcome to the October. It's October already. Wow, October, mid-fall, or at least beginning of fall, however you kind of want to count it around here, of the Grand Strand Astronomers meeting here in the greater Myrtle Beach area. We're actually live at Coastal Carolina University here today. Of course, we have a lot of people up here virtually as well from various places. We did say we would do some live meetings during the year and see how that goes, but we're always going to be doing virtual meetings, right? Which I realize is useful for those of you that have to travel far. I know some of you live in the south part of the Strand. That takes a while to get here. And I also know some of you are from Charleston, which takes even longer to get here, and it'd be an awful long drive back. So, but anyway, thanks for everybody for coming out. Before we get started, I'd just like to do a couple of things. And Patrick, if you can excuse us for just a few minutes, or I mean, you can stay on, but what we're going to do, a couple things, just kind of go over a couple things. We had a very good observing session actually in September at Hampton Plantation. So we caught a really good night, and it was definitely well worth going out. It wasn't too cool, and the conditions were very good. We actually had a fair number of people out, some people both from the Low Country Stargazers, the Charleston group, and our group. So that went pretty well. Here's hoping we get good luck at the end of the month for our observing session. It'd be great to get 2 in a row. I don't think we've had 2 in a row yet, but hopefully we'll get 2 in a row, and we'll get some good conditions and be able to get some good and some good observing. So Hampton Plantation continues to be very willing to work with us, and they're continuing to work on the dark sky site. We can talk a little bit more about that after the meeting or after the presentation. There are some things that we'll probably need to work with Hampton Plantation on. So if everybody could kind of just hang around after the presentation for a few minutes, and we can talk about that. So that's upcoming. And of course, we have our November meeting upcoming as well. That'll be the second Thursday of November. Now, the November observing session is actually early because the 4th Saturday is actually over Thanksgiving. So I think we bumped it back one, if memory serves. I think Gerald is maybe checking it. Is it right now while I talk? He's my back checker. Yeah. So on the 22nd. So just so everybody knows, the moon conditions are pretty good. Hopefully it'll be nice that day as well. So sorry, it's October 20. I'm sorry.
I think it's sooner than that. October 22nd.
So October 22nd is our observing session for this month, right? So we're also going to try to still get an observing session going here in late November, maybe early December, but probably try to shoot for late November, maybe that week after Thanksgiving for Mars. Mars will be approaching opposition. It'll be very well positioned, and we like to get something going here at Coastal Carolina University where there's lots of space and we can get a lot of crowds in. It'll be a public observing session. So those are a couple things. Also, before people drop off, well, actually, we can do that after the speaker. Why don't we go ahead and if no one else has any announcements they want to make to the group, we'll go ahead and introduce our speaker. All right, I'll take that as a no. So we're very lucky tonight. We have a great speaker. We have Dr. Patrick Schroethart from the North Carolina Museum of Natural Sciences. I see his background is actually the museum building. His office, I know the Astronomy and Astrophysics Lab, of which he's an astrophysicist with the Astronomy and Astrophysics Lab, is actually right by that globe. So he can, kind of basically, he's sort of right in that general area. So Dr. Schroethart works on galaxy structure, and come to talk to us today about the Milky Way and what we know and how we know it. So without further ado, I'll turn it over to Patrick and let him sort of take the show.
All right, thanks. All right, I'm going to share my screen, and if you can't see it, let me know. All right. All right, yeah. So I'm Patrick Troithart. I'm one of the two astronomers that work at the North Carolina Museum of Natural Sciences, and like Ian said, I am interested in galaxy structure, basically morphology and dynamics. So I'm interested in the shapes of galaxies and the underlying physical processes that create those shapes. And so what I'm interested in working on is studying the shapes of galaxies and determining what those shapes can actually tell us about some of the things that are harder to measure within galaxies. So, for instance, like black holes and dark matter content, things like that in galaxies. But what actually, so the Milky Way isn't actually a galaxy that I study, because the Milky Way is actually unique in its own way, in that it's a galaxy that we live in, and the way to figure out things about the galaxy we live in is actually in my opinion, harder to do than trying to figure out things in galaxies outside of our own. But that being said, I mean, the Milky Way is very interesting, and it is fun to talk about. So let's get started here. So I'm sure, being astronomers yourselves, people have seen the Milky Way, right? So people are kind of familiar with this image. Obviously, this is a lot of false color in this, just to highlight things. This is not really a good coloration of what the Milky Way looks like. So looking online, kind of perusing online, these are some images that I found that look a little more realistic in their color, in my opinion. And so, for instance, if you look at this bottom right image, you can see there's actually part of the Milky Way is actually a little bit more yellowish orange. And if you look toward away from that central part, things look a little bit more blue. And obviously, you see these dark lanes in there, these dark stripes cutting through this like hazy band of stars in the sky. So if we look at the Milky Way throughout the night, this is kind of what it looks like. And I apologize if this is jumpy, because my computer doesn't have it doesn't have a very good video card, and it's probably streaming over the internet. It's probably not great either. But you can see right here, this is the Milky Way, and you can see this is like away from the bulge, away from the central part of the Milky Way, and you can see it looks kind of blue out here, and you start to see a lot more dust. And then you see the yellowish orange region right here, and that's the bulge of the Milky Way. That's a central part. And you can see it just continues on out here, out toward the far right. And so this is just a different perspective that I just found to be really great. A little, in my opinion, a little more realistic, where the sky is stabilized and the Earth rotates. But again, you can see the Milky Way here. You can see the bulge. You can see the dust blocking the starlight. But if we subtract out the Earth and we just look at the sky itself, and we look at, basically a 360-degree view of the sky in the Milky Way, this is what it would look like. And so again, if you look out here at the edges, it looks very blue. So these are basically hot, massive stars. And then here in the middle is more yellowish orange, and that's the bulge. That's the central region of our own galaxy. And these dark bands that you see here, this is all dust, and this is all dust blocking out the starlight behind it. So basically, all this hazy band that you see in the sky is just billions and billions of stars so far away that you can't actually resolve them. So just again, it's like if you're if you're on the highway at night and you see a point of light way out in the distance, on this very flat straight road out in the middle of nowhere, right? And as you get closer to that point of light, all of a sudden now you can see that point turn into 2 points, right? And those are actually the headlights of a car, right? So if the car is far enough away, you're not going to be able to resolve those headlights. But once you get closer to it, then you can actually see it. And so the same thing is true here. The stars are so far away that you can't resolve each individual star anymore. They just look like a band of light in the sky. But what you can see, so you see the Milky Way, and you can actually see two other things here. You see this little blob down here, this little blob here, and I believe this little blob right here. And these are the only things that you can see with that are outside of our own galaxy that you can see with the naked eye. So this is the Large Magellanic Cloud, the Small Magellanic Cloud, and then this is the Andromeda Galaxy. And these are the only. So when you go out at night and you just look with your naked eye at the sky, everything that you see is within our own galaxy except for those three objects. And really, these two objects down here you can't see from the northern hemisphere. You have to be in the southern hemisphere to see them. So it's really just the Andromeda Galaxy. So like I said, the Milky Way is just composed of billions of stars. So we estimate there are about 200 billion stars in the Milky Way, and that the Milky Way, oops, oh, and so again, so that's a lot of stars, uh, but it's also the Milky Way is enormous, and so the best way to kind of talk about the size scale of the Milky Way is to talk about it in terms of light speed. Um, so obviously, light moves incredibly fast, so it can cover a large distance in a short amount of time. And so this video is made by James O'Donoghue, who makes uh, just really great astronomy related videos to kind of put things into perspective. And so this is basically just a beam of light orbiting the Earth in 7.5 seconds. And so that's basically shows you how fast light can travel. This other video he made shows you the real light speed, light travel time between the surface of the Earth and the surface of the Moon. So it takes about 1.25 seconds for light to leave the Earth and reach the surface of the Moon. So it takes about 2 seconds for a signal to reach the Moon, bounce back, and come back to us. So the distance between the Earth and the Moon is vast. And so there is a time delay between sending a signal to the Moon and receiving that signal immediately back to the Earth. Okay, and that's the nearest body to the Earth. Okay, so that in itself should already give you a hint as to how big the galaxy is. And so this is the light travel time of a beam of light from the sun going to the Earth. So the light travel time is the scale. The objects are not. The distances are. And so we're not going to watch this whole video. We're not going to watch this beam of light travel 8 minutes to the Earth. But it does take light about eight minutes to reach the Earth from the sun. So it's again, the distances even within our own solar system are huge. So now that you kind of have a sense of scale as to how widely separated things are, even within our own solar system, our galaxy is so large that we estimate that it takes light about 100,000 to 200,000 years to travel from one side to the other. And the reason why that range is so wide is because we don't really have a good idea as to the actual extent of the Milky Way. At one point we thought it was 100,000 light years in diameter. Then there was some other papers that came out that actually doubled that size. So I'm putting in both ends of the estimate range, of the range there. But basically, the Milky Way is huge, and because of that, there's no way for humans to basically get outside of the Milky Way to actually view it, to actually view its structure and to understand exactly what it is, right? So, like the work that I do is galaxies outside of the Milky Way, and so that's a lot easier because you can see all of those galaxies outside of the Milky Way, but you don't get all of the high resolution data of what are the stars, what are potentially individual stars doing and things like that. Can't really do that, but you can look at the structure of these galaxies. But being stuck in the Milky Way makes it a lot more difficult to figure that out. One good analogy I've heard about studying the Milky Way is if you imagine that you're stuck in your house in your subdivision and you're trying to map out the streets in your neighborhood. So that becomes extraordinarily difficult. I mean, you can look out your windows and you can potentially map out the street in front of your house, maybe map out the street, that your backyard neighbor is on or something like that. But then if you want to map out the rest of the neighborhood, it becomes a lot more difficult and you have to be really creative. So, potentially you'd have to look out of your window into a neighbor's window, see a reflection off of a teapot to an adjacent window, and just kind of figure things out from there and do some math and be really creative as to how you actually map that out. And so essentially, that's kind of what astronomers are doing with the Milky Way, in that we can't get outside of the Milky Way. We can't really go anywhere in the Milky Way. We're obscured by dust everywhere within the plane of the Milky Way. So we have to look for windows. We have to be creative as to how we can actually determine the structure and things like that within the Milky Way. Okay, so what is the Milky Way? So we basically, where did the term Milky Way come from? So we give a lot of credit to the ancient Greeks in terms of astronomy. I mean, a lot of cultures were doing astronomy, years, thousands of years ago. But we give a lot of the credit to the Greeks because a lot of what the ancient Greeks did was uh, basically studying the heavens for the sake of understanding them. So a lot of other cultures, what they would do is they would study the heavens, but not really to understand what was happening, but more to make predictions and to, um, further legends and things like that. Make predictions in terms of, like when to plant crops and things like that, and like astrology and other less educational things. I would say. But the ancient Greeks, we give them a lot of credit just because they really wanted to understand the universe they live in. And so one of the things that we give them credit for is the term Milky Way is that's where we get the name of the galaxy from. So they called it Galaxias Koukalos, which means Milky Wheel or Milky Circle. And so we took that from the ancient Greeks, and now we call the band in the sky the Milky Way. And so the reason why they called the legend that went with that was that Hera was or basically Hera was sleeping, and Heracles was put upon Hera and started feeding on her, and she woke up and pushed him away, and milk spilled across the sky, and that's how they got the Milky Way, and that was the legend that the Greeks came up with. And then 1,000 years later, the Romans essentially had a very similar story, only in this case it was Juno and Hercules, but essentially they're the same gods, and it's the same story itself. It's just 1,000 years later. So like I said, I mean, different cultures had different interpretations as to what the Milky Way is. So I mean, these are just a selection of different cultures and what they thought it was. So like the Armenians thought it was a straw strewn across the sky. Like the Maori thought it was a canoe, things like that. But actually, my favorite one is this Finnish one here called the Pathway of the Birds. I actually like this one because this one actually has like a little hint of science to it. So the Finns actually identified that birds seemed to follow the path of the Milky Way as they migrated. So they thought they actually used the Milky Way to migrate from north to south or south to north. So I actually find that to be pretty interesting. That is more observational in nature. So like I said, the ancient Greeks really started to think about the universe they live in and what is the Milky Way. And so the first real thought about the Milky Way that was recorded was by Democritus in about 400 BCE. And he thought, well, maybe what we're looking at isn't actually milk in the sky. It's not actually, just a light band in the sky. Maybe what we're actually seeing is just, lots and lots of stars, but they're just so far away that we can't actually separate the stars out individually. And so he was the first one to think that what we were looking at was actually unresolved stars in the sky. So it wasn't until 2,000 years later, again, there was the ancient Greeks didn't have the technology to actually figure this out. They came up with these ideas, but it was really difficult for them to follow through and actually identify what these things really were. But so it wasn't until 2,000 years later that Galileo turned a telescope to the heavens and looked, basically into space and saw, okay, there are a lot more stars in the sky than we can see with our naked eye. And so that basically led him to believe that, okay, what we are seeing in the Milky Way is unresolved stars, that the Milky Way itself is not just a hazy band of light, that band of light is actually individual stars that are so far away that we can't resolve them individually. So that took about 2,000 years to figure out. So then in the 1750s, so about 100 years later, two scientists, two mathematicians, they started thinking about the Milky Way, and they so this is Thomas Wright and Immanuel Kant, and they thought that, okay, maybe what this band in the sky is telling us is that we actually live within a large disk of stars, that there aren't just stars everywhere in this, and equal in all directions, that we actually live within a disk of stars. And so the idea is that if stars were uniformly scattered throughout the sky, that we lived, somewhere within a sphere of stars, that no matter which way you look, basically the distribution of stars would be essentially the same. So if you imagine, being inside of a beach ball and just punching holes within the beach ball, and you look out at the lights, you would essentially see the distribution of these pinholes equal in essentially every direction, no matter where you are really in that beach ball. But if you're inside of a hockey puck, if you look along the plane of that hockey puck, you're going to see a lot more material within that plane than if you look out from the plane of that hockey puck. So if you look, slightly up and slightly down, you're going to see some of that material, but you're not going to see as much as if you're looking straight through the plane of the hockey puck. And so this is why we think we live in a disk of stars. Okay, so this video just kind of gives you an idea of what we think the Milky Way actually looks like. Okay, and so when you look at it face on, you can see that there's spiral structure. There's the bulge in the center, and then as you rotate it to edge on, you can see the dust kind of obscuring the starlight. But you can also see that it's very, very thin. That the galaxy itself is a very, very thin object. And so really the ratio of diameter to thickness for the Milky Way is about the same as stacking two DVDs on top of each other. So the spiral galaxies like the Milky Way are very, very thin objects. Their diameters are enormous compared to their vertical thickness. So after Wright and Kant kind of basically talked about, okay, this is why we think we're in a disk of stars. William Herschel then thought, okay, well, where are we within this disk of stars? Like, where do we exist within this disk? And so this is kind of sort of coming off of the heels of the Keplerian, well, basically coming off of the heels of like, okay, we no longer live in a heliocentric universe. We know that the Earth now orbits around the sun, so we're not really in a special place within the solar system. Are we in a special place within the Milky Way? So what William Herschel wanted to do was figure out where we were in the Milky Way. And are we in a special place? Are we in the center of it? Or, are we at an edge? Are we, some distance away from the edge? Where are we within this disk of stars? And so what he wanted to do was essentially just count stars in both directions along the disk of the Milky Way. And essentially, if we're in the center, right, you would see an equal number of stars in both directions. Or if you're closer to an edge, then you see more stars in one direction and less stars in another direction, right? And so he assumed that the number density of stars in the Milky Way is constant. So essentially, there's one star per square foot or something like that, right? So the number density was constant. So that was his assumption. So this is the diagram he published of all the stars that he can measure the distances to, and this is where the sun is. So that little slightly larger asterisk that you see in the center there, that's the sun. And so basically what he found was that we're in the center of the Milky Way. So we came off the heels of we no longer live in a heliocentric universe, so now we live in the center of the Milky Way. So now we're in a special place in the universe again, which again seems kind of weird. Like, why would that happen? But so the reason why this happened is because he was unaware of dust. He didn't know that dust existed and that dust was in the plane of the Milky Way and that dust obscures starlight. He didn't know this, but he actually mapped it out. So that wedge that you see there is actually dust blocking out the stars from behind it. And so you can see the stars above and below the dust lane right there. And you can see that they reach much further out than, for instance, right where the dust lane basically starts obscuring the stars. So this is the reason why basically his method didn't work. So that was the 1800s. And then about 100 years later, there was an astronomer named Henrietta Leavitt. So she was actually working as a computer, so one of these people who just does mathematical computation. But she was really, she studied astronomy. She was really interested in astronomy. and she was working on, basically working on stars, and she came across this basically unique class of stars called Cepheid variables. And this is what she's most famous for, is identifying these stars, which become very, very important. So these Cepheid variables are stars that essentially inflate and deflate at regular intervals. And as they do that, their brightness changes. And what's interesting about them is that their rate of pulsation, the rate of the brightness pulsation, is directly related to how intrinsically bright they are. Okay, so this is basically a plot of Cepheid variables here. And so essentially, if the pulsation period is very short, then the intrinsic luminosity of these stars is pretty small. And if the period is very long, then the intrinsic luminosity is very bright. Okay, so what this means is that you just have to find these pulsating stars, figure out the rate of pulsation, and then you know how intrinsically bright these stars are. Okay, so this is critical. This is really important because these stars now act as standard candles. Okay, so what a standard candle is if you just have, if you go to the store and you buy a bunch of the same candle, right? They're all standardized, they're all the same. And you light them all, you ignite every single candle right in front of you on your table. They're all going to look to be exactly the same brightness. But now you take a candle and you walk down the street and you put it in your neighbor's yard. You know how intrinsically bright that candle is, but now when you're standing in your yard and you're looking at that candle, it looks much dimmer. And so you can calculate the difference between how intrinsically bright it is and how bright it looks, and that will actually give you the distance to that candle. Okay, and so this is exactly the same thing with these Cepheid variables. Because we can watch them flash at a certain interval, we can determine how intrinsically bright they are, and then we just measure how bright they look, and we know the distances to these stars. So we can use these to actually map out distances to different places within the galaxy, and this becomes very, very important. So she found these things, but it wasn't until Harlow Shapley came along that he actually figured out a way to use these to map out the Milky Way. And so there are clusters of stars in the Milky Way called globular clusters. And these are clusters of stars where basically a cluster of stars is a group of stars that are all born from the same giant gas cloud, pretty much all at the same time. They're just born of different masses. But they're all born at the same time from the same gas cloud. And so these globular clusters are actually formed not only in the plane of the Milky Way, but also outside of the plane of the Milky Way. So they're basically what's thought to be is distributed kind of spherically around the Milky Way, within a sphere around the Milky Way. And so what Shapley thought was, okay, well, if we can find these Cepheid variables in these globular clusters, we can determine the distances to these clusters. We can basically map out their positions, and the center of the distribution of these clusters should be the center of the Milky Way. Okay, so that's exactly what he did. So, these two images here are basically the same thing, but I'm going to reference this center one here. So basically, all of these magenta dots are different globular clusters, and so here we are right here, and he just mapped out the distances to these globular clusters, and he created this distribution, and he found the center of the distribution, and he said, okay, here's the center of the distribution. This is the center of the Milky Way. So now in 1917 or so, we now know that we are not in the center of the Milky Way, that we're actually about halfway out from the center of the Milky Way to the edge. So we're about 8.5 kiloparsecs from the center of the Milky Way. So we're not in a special location anymore. All right, so nowadays, astronomers, when we look at the Milky Way, we now know that there are different components to the galaxy, and that we kind of just break them down into like three main components. So we have the bulge, which is just the central kind of spherical region in the Milky Way. So that's this part right here. This is composed of older stars. And then we have the disk region, which is this component here, which is composed of like old and young stars. But the main part, the thin disk right here, This is composed of younger stars. So this is where all the star formation happens. This is where you find a lot of the younger stars. And then outside of the disk and the bulge, you find the halo. And this is where we find globular clusters. And then this is also where we find a lot of this dark matter that I'm going to talk about in a little bit as well. So the three main components to the Milky Way, or to really any kind of disk galaxy, is the bulge, the disk, and the halo. Those are the three main components. Okay, so now we know where we are in the Milky Way. We know that it's a disk, but what is the structure? Is it a uniform disk, or is there actual structure within this disk? And so that's really hard to determine just by looking at the sky and looking at that hazy band in the sky, right? So I mean, there's dust, there's just a hazy band of stars, but what's the distribution of material within that hazy band? So what astronomers have done is they've what we can do is use Doppler shift and measure the rotation rates of basically gas clouds within the disk. So what we can do is we can look within the disk and look for gas clouds at different distances and measure their basically their orbital speed around the disk. Okay. And so if there's an even distribution of gas clouds from basically where we are all the way to like the other side or to the edge of the disk, then basically what you would see is essentially an even distribution of like light intensity and velocity and things like that. So you just see it like a nice smooth line of gas intensity essentially as you're looking throughout the disk. But what we've found is that that's actually not the case. We actually don't see this uniform distribution. We actually see peaks and valleys as we look at different distances throughout the disk. And what this tells us is that there are concentrations of gas, there are concentrations of gas clouds, and then there are regions of basically rarefied regions of gas clouds. So there's basically no gas, very little gas between these high intensity regions. And so what that means is that the disk is not uniformly distributed from us to the edge. And what we think is happening is that there are actually spiral arms within the disk. So like other galaxies that we see, so like the Andromeda galaxy, all these other disk galaxies that we see, we think that the Milky Way actually has spiral arms just like any other galaxy. And it's because of this lack of uniform distribution of gas throughout the disk. And so this is just a cartoon kind of mapping out where we see different gas clouds. So here we are. So this little yellow dot right here, this is where we are at the sun. And so you can see we're on a little spur of an arm right here called the Orion spur. And then you can see these different colored arcs that you see here. These are all different, what we think are different arms. These are, we find gas clouds here that seem to be associated with each other. And we seem to, when we associate those with a single arm. So you can see here's the Perseus arm, and then we see these outer arms out here. And then you can see these dashed lines right here. This is actually where we can no longer measure anything. This is where we can't see anything anymore because it's either obscured by dust or too far away. It's just things we can't see anymore. And so, for instance, here, this cone that you see here is actually the shadow of the galactic center. So we can't see through the galactic center to the other side. So we infer that, there's no weird discontinuity between the arm that we see here and the arm that we see here, that it actually continues on in the solid structure. So we just make assumptions about the opposite side, that it's not somehow asymmetric, that it's actually like the Milky Way is actually a symmetric structure. So this is a little better, a little more scientifically accurate interpretation of it. So again, now it's flipped over. So right here's the sun, here's the Orion spur, here are these arms. You can see the dust lanes are also within these arms here. So you got the stars and the dust here. And then between the arms, there's not a lot going on. You have some stars, but really you have some stars, dust and gas, but it's much far less than what you see in the actual arms themselves. But one interesting thing, so I'm actually really interested in the bar structures that are found in the centers of spiral galaxies, and about 70% of spiral galaxies. And so what's interesting is the Milky Way seems to have one of these bar structures. actually not just one, there's evidence to support that there's actually two bar structures within the Milky Way, one kind of overlapping the other and offset by a little bit, which is weird because every galaxy I've looked at, that doesn't happen. I've never seen that in another galaxy. But the data seems to suggest that there's basically a shorter, fatter bar and then a longer, thinner bar, just kind of slightly rotated away from each other. In my opinion, I think, given more data, one of those bars is going to go away and we're going to be left with only one of those. But as of right now, I think the data suggests that there are two bars, which was unique. And so these are galaxies outside of our own, but these are galaxies that basically seem to have almost the same structure as the Milky Way. So if you were to get outside of the Milky Way and look back at it, we think that it would look like one of these galaxies that you see here. And so again, you see the bar structure here, you see the bulge, you see the spiral arms, but you also see this other structure here. You see this kind of ring surrounding the bar. You can see the same thing right here, this ring surrounding the bar. And so this is actually what we call a resonance feature from the bar. So the bar is rotating, and because it's not a symmetric object, as it rotates, it actually kind of redistributes material within the disk and creates these ring structures around the ends of the bar. And so we think that the Milky Way actually does this as well. Okay, so if we have spiral structure within the Milky Way, and other galaxies have spiral structure, and these galaxies have been around for a very, very long time, how is that spiral structure maintained over, essentially billions of years? Over many, many rotations, how is that spiral structure maintained? Well, the first idea is that, okay, well, maybe the entire Milky Way rotates like a record, and that it rotates as a solid object. And the spiral arms are just kind of painted on that record. And as the record rotates, that whole spiral structure is just going to rotate as the galaxy rotates. Well, by measuring the gas clouds, the rotation rates of gas clouds, we know that's not true. The galaxy does not rotate as a solid object. It doesn't rotate as a record. There's actually what's called differential rotation within the Milky Way. And what that means is things closer, basically gas clouds closer to the center of the Milky Way orbit faster than gas clouds that are further away. So it's essentially like, like on NASCAR. If you're on the inner track, you're going to go around faster than if you're on the outer track. Okay, so the video here on the left is wrong. So that's not how the Milky Way behaves. The other idea is, okay, well, if we have differential rotation, that can basically create spiral structure on its own, because basically if you just start out with a bunch of stars kind of in a line radially out from the center, and if the stars on the inside are moving faster than the stars on the outside, you'll automatically get spiral arms out of that. But the issue is that over time, as you go through many, many rotations, that spiral structure keeps winding up and winding up and winding up and gets tighter and tighter until you can no longer see spiral structure anymore. And so that's the central video right here. So basically, as time goes on, the arms get so wound up that you actually lose their definition, that you can't actually see them anymore. So this is not what happens either, because we still see spiral structure within the Milky Way and other galaxies. So what we think is happening is essentially an idea that we call density wave theory, in that gas clouds are moving into and out of regions of high density. And as they move into these regions of high density, they collapse, they ignite and form new stars. They light up this high density region. And then those stars burn out, basically go supernova, turn into gas clouds again. And then those gas clouds move out of that high dense region, pass through, the rarefied regions between the dense regions, get back into another high dense region, again, ignite, form stars, and reignite those arms again. And so this is what we think is actually happening within our own galaxy and other galaxies as well. So it's actually gas clouds moving into and out of high dense regions. Okay, so that may not make a lot of sense, but there's a really cool video that I found online that kind of shows you how that works. So if you look at all these dots, and again, this may not turn out great over streaming online, but each one of these dots represents a gas cloud orbiting around in a circular orbit. So now what this author is doing is stretching out these orbits into ellipses. And again, they're all orbiting around And now you rotate these, and now what you do is you rotate these ellipses a little bit, so a little further in this, more in the center and less on the outer edges. And as you do that, you automatically create these high dense regions. So now all of these gas clouds, all of these dots are orbiting into and out of regions of high density. And as they enter these regions of high density, all of these gas clouds are going to collide and form new stars and then ignite and form these arms that you see here. And so you can create these really beautiful, what we call grand design spirals from that, just by having essentially elliptical orbits offset from each other. And by doing that, you create spiral structure and density waves. Okay. All right. So this is how we get, this is essentially the structure of the Milky Way in the disk. But what's happening in the halo of the Milky Way? So one interesting thing that happened in the 1970s was Vera Rubin was looking at spiral galaxies, so one like this, and she wanted to measure essentially the rotation rates of these galaxies. And so when you look at a spiral galaxy like this, obviously it's much brighter in the center, and then as you get further away from the center, the brightness decreases until it essentially reaches zero, right? And so by looking at this, you would assume where it's brighter, you would have a lot more mass. There's a lot more material where it's brighter. And when you get out here, further away from the brightest objects, there'd be a lot less material out there. There'd be a lot less stars, so there'd be a lot less material. And so what you would expect is if you measure the rotation rate of, these stars, these gas clouds, things like that, from the center out toward the edge, as you're measuring the rotation velocities, what you're doing is at every radius that you're measuring a rotation velocity, you're measuring the mass within that orbit. Okay. And so as you get further and further away from the center, you're enclosing more and more of the galaxy. But as the brightness goes down, you're enclosing basically the same amount of mass, just further and further away from the center. And so what you would expect is that the stars furthest away from the center, the rotation velocities would decrease because essentially they're enclosing the same amount of mass, but they're just further away, so their orbit is going around much slower to stay in a circular orbit. But what she saw was that as you move further away from the center, the orbital velocities essentially either stayed flat or increased. And what that means is that all those radii that are encompassing the galaxy are enclosing more and more mass. But it's enclosing mass that's not giving off light. So what that means is that there's mass there that we can't see, but it's behaving gravitationally. And this is this is very important. This is the first indications of dark matter within galaxies. And this is essentially because we can watch the rotation rates of gas clouds and stars within a galaxy, and we know that they're essentially not decreasing with radius, they're actually staying constant or increasing with radius. And that tells us that there's some kind of matter out there that's not glowing that we can't see. And that's known as dark matter. And so if you look at a galaxy, so this galaxy here on the left is essentially, both of these galaxies are showing you like the density wave structure of a spiral galaxy. But the galaxy on the left has no dark matter, and the galaxy on the right has dark matter. And you can see the rotation rates of essentially of the material on the outer parts of the galaxy, and you can see that the material is moving much slower on the galaxy on the left than the galaxy on the right. Okay, and so dark matter, this is the reason, and this is the reason that this is happening, is because of this invisible matter that we can't see, that we can't detect other than through gravitation. All right, and so this is just a little cartoon diagram showing you essentially what's known as the rotation curve of the Milky Way. And so here's the center, here's the rotation speed, here's where the sun is. And so essentially, we don't really expect anything, we really don't expect to see any kind of effects of dark matter where we are. But as you get further away from the center, all of a sudden here at about 15 kiloparsecs, this is where things start to diverge. So about here is where we would expect, if there was no dark matter, we'd expect the rotation curve to decrease, but instead we see it kind of flattening out and continuing on. And so this is actually an indication of dark matter within our own galaxy. And so what we know now is that of the total mass of the Milky Way, 90% of it is dark matter. Only 10% of it is the matter that we're familiar with, in that, like, what we're made out of, what the tables are made out of, what the stars are made out of. That makes up about 10% of the entirety of the Milky Way. 90% is actually dark matter. All right, so that's essentially the outer parts of the galaxy. That's where the dark matter is most evident in the outer parts of the galaxy, in the halo section. But now if we zoom into the nucleus, there's actually some interesting things going on there too. So one weird thing that you can see in this image, maybe if you can see it. So you can see the Milky Way right here. So this is actually an X-ray image. An X-ray or gamma ray image of the Milky Way. Actually, I think it's an X-ray image. And so you can see all this bright material right here in the plane of the Milky Way. This is essentially where we see a lot of supernova remnants. We see neutron stars, things like that. These kind of high energy events that create a lot of X-rays. And so we see a lot of that in the plane of the Milky Way. The weird thing is that you see some faint regions above and below the plane right near the center of the Milky Way. So you can see this kind of arc right here, and this kind of blob up here. These are little blobs perpendicular to the plane that are emitting X-rays. And so this was weird when they first found this. This was actually pretty strange. And so what we now think it is, we now call them the Fermi lobes. These are actually giant lobes of X-ray emission, or the remnants of giant lobes of X-ray emission perpendicular to the plane of the Milky Way. And this is what we think they look like, or what they used to look like. And so what caused these giant lobes to occur? Well, by looking at other galaxies, we see that some galaxies actually have jets of material shooting out from the center of the galaxy perpendicular to the plane of the disk into intergalactic space. And when they do that, they hit this intergalactic medium, this like very rarefied, few hydrogen atoms per, parsec medium, but it hits it with such force that it actually shocks that intergalactic medium and causes like a shock wave, a shock front to it, and creates these bubbles. And so this is a galaxy called Centaurus A, where you can see the jet of material here, and then it interacting with the intergalactic medium and creating the upper part of this little bubble here, and you can see a shock front right here on the bottom part. Okay, so what's creating these jets? Well, if we zoom in very close to the nucleus of the galaxy, what we're going to see is what's known as a dusty torus. So it's essentially a donut of dust, very, very close to the nucleus of the galaxy. Within the bulge, within the core of the galaxy, near the very heart of it, you're going to see a dusty donut. And so if we zoom in within that dusty donut, this is what you're going to see. So you see this, you're going to see a disk of material here. And so here's the wall of the donut. Here's, the rest of the galaxy out here, but here's the wall of the donut, the wall of the torus. And all this material is spiraling in onto what's known as a supermassive black hole. And so these are black holes that range from millions to billions of times the mass of the sun. And so as this material is basically falling onto this supermassive black hole, there's essentially the material on the inside track is moving faster than the material on the outside track. And so essentially, let's just say it's hydrogen gas, right? And as those hydrogen atoms are moving on the inside track faster than the outside track, you're going to get viscosity. You're going to get friction between the inside track and the outside track. And as you get viscosity, you get heat, which creates energy. And essentially, it's going to turn it into a plasma. And when that happens, you have basically free-floating protons and free-floating electrons. And so now these charged particles are moving, which create a magnetic field. And then these charged particles will get trapped in these magnetic fields and essentially get accelerated outward with such velocity that essentially they form these jets that shoot out from the very nucleus of the galaxy out into the intergalactic medium with such high velocity that when it hits the material, it actually creates gamma rays and X-rays. So what you're seeing is basically a supermassive black hole that's, compared to the size of the galaxy, minuscule, creating so much energy that it's visible at basically intergalactic scale. And so those Fermi bubbles that we saw, we think those are remnants of the supermassive black hole within our own galaxy being active, and that material was at some point material was falling onto the supermassive black hole. We had those jets slamming into the intergalactic medium, but at some point, basically the material stopped falling into the black hole, or there just wasn't a lot of that material left, and those jets kind of shut off, and we're just left with the afterglow of those bubbles. Okay, so that was kind of some of the early evidence for a supermassive black hole within our own galaxy. But then in the early 2000s, some astronomers got creative, and they decided to spend a lot of time observing the very center of the Milky Way. And what they did was they tracked the orbits of a few stars at the very heart of the Milky Way, some stars that they could actually see. And what they found was that some of these stars were orbiting around an unseen object. So each one of these colored blobs here is a star, and that the white star object is the unseen object that they're orbiting around. And so by mapping out the orbits of each one of these stars, each star then gives you the orbit of each star then gives you the mass of the object that it's orbiting around. So if they mapped out the orbits of 20 stars, they have 20 independent measurements of the mass that they're orbiting around. And so what they found was that the mass that these stars are orbiting around is about 4 million times the mass of the sun. And it's enclosed in such a small volume that the only thing it could be is a supermassive black hole. And so this is, at the time, this was then the best evidence for a supermassive black hole in the center of our own galaxy. Okay, yeah, so it's 17 times the diameter of the sun and a mass of 4 million times the mass of the sun. So this is the only thing it can be is a supermassive black hole. And so the previous little animation I showed you was kind of like a cartoon image of that. And this is the actual data taken over those years of those stars. And you could see, like, for instance, this star right here orbiting around that supermassive black hole. And the interesting thing too is that you can see as the years went on, as they switched out the instruments to better instruments, you can actually see the resolution get better too. I find that to be pretty cool as well. And then it wasn't until a couple of years ago now that we actually had our first direct images of the supermassive black hole at the center of our own galaxy. And so the Event Horizon Telescope managed to actually image the region around the black hole. So the evacuated region that you see right here, that's essentially where the supermassive black hole is. And this is the remnants of that accretion disk, that disk of material that's falling onto the black hole. This is the remnants of that. That's the afterglow of that. And you can see that looks very similar to the first image they took of the supermassive black hole in M87, which honestly I think was an easier target than the black hole in the Milky Way, even though it's in a different galaxy. All right, so where did the Milky Way come from? So how did we end up with the Milky Way? And so that's actually a really interesting question, because in this timeline of essentially the universe here, so we have the Big Bang here at this left end, and then we have present day here at the right end, and it's about 13.5 billion years from left to right. Here at about 400 million years, this is where we see the first stars forming. And it's really not that long after the first stars form that we also end up with the first galaxies. And so that's really interesting, in that we don't know how galaxies can form so quickly. And also the other interesting thing is that as soon as these galaxies form, we're also seeing evidence of supermassive black holes within these galaxies. And it's really unclear how supermassive black holes can form that quickly. And so that's an active topic of research, is trying to understand how these supermassive black holes can form so quickly very early in the universe and just kind of continue along with the galaxy as it evolves. So what we think happens, essentially the dominant idea as to how galaxies form is something called hierarchical merging. In that essentially you start out with gas kind of obviously not completely equally distributed everywhere. So there's some fluctuations, some higher dense regions. And then those slightly higher dense regions kind of condense and form slightly denser regions. And those are attracted by gravity, and then they kind of come by each other and then get attracted, kind of merge together and things like that. But essentially over time, what happens is you end up with larger and larger objects. And some of these small objects that are left over merge with these larger objects. So essentially what hierarchical merging is kind of a bottom up. It's essentially like an inverted family tree where you have a large number of small objects kind of all merging together to form one large object in the present day. So if you just imagine a family tree upside down, rather than having all your distant ancestors at the top, they're at the bottom and then they come up to you where you are now. And it's essentially how we think galaxies like the Milky Way form. And so in this video here, you can see this is actually showing you hierarchical merging, and you can see the spiral structure forming, and you can see still some small mergers happening with this galaxy. And at some point, you can actually see a bar forming in the center of this galaxy as well. And so this is a really, really good computer simulation of a small region of space forming a galaxy. But the James Webb Telescope is actually, one of its missions is to actually tell us more about how galaxies form. So obviously the James Webb Telescope is going to be able to look further back in time and look at some of these very early galaxies. And the hope is that we'll actually see direct evidence of hierarchical merging early in the universe. And that will actually then tell us, okay, this is actually how galaxies form the way they, form early in the universe, and this is how they became what we see today. It's through this merging process. And so this is, I'm sure people have seen a lot of these James Webb Telescope images, but this is just to kind of give you a taste of the difference in, how distant, basically what James Webb is able to see. So the lower resolution image, the one that shows less objects, is a Hubble image actually, and the high resolution image, the brighter image with a lot more color in it, that's actually a James Webb Telescope image. And you can see there's a lot of background things that kind of pop out in the James Webb image, and those are all much more distant galaxies that Hubble just can't see, just because it's not within its wavelength range anymore. But James Webb is able to actually see these distant objects. All right, so finally, what is the fate of the Milky Way? So what's actually going to happen to the Milky Way? Well, it was not that long ago, I mean, I guess at least within the last 10 years, that we were able to accurately measure the velocities, the velocity vectors of our nearby galaxy. And what we found was that the Milky Way and the Andromeda galaxy are actually on a collision course, and that after a few billion years, they will actually collide with each other and merge and form a new galaxy. And so this is a computer simulation kind of showing what that process is going to be like. And you can see the two galaxies have already kind of collided. They've scattered stars everywhere. And now the two cores of the galaxies are going to merge together. And then you're left with so before the galaxies were very blue, and now you're left with a very yellowish orange object with essentially no structure to it. The spiral galaxies have a ton of structure, a ton of blue stars, and what's left over is this essentially elliptical galaxy. This galaxy that's not forming new stars, all the structure is gone. Essentially, it's just a blob of gravitationally bound stars. And so eventually what's going to happen is the Milky Way is going to merge with the Andromeda galaxy, and then we're going to be left with no longer a spiral galaxy, we're going to be in an elliptical galaxy. Okay, so if you're around in about 4 billion years, This is essentially what they think the sky is going to look like. So in present day, here's the Milky Way in the sky. Here's the Andromeda galaxy, this little object in the distance. And then in about 2 billion years, the Andromeda galaxy is going to look much, much brighter. You're definitely going to be able to see it at night. And then in 3.75 billion years, then things are really going to start to happen. Now Andromeda is going to be so close that it's actually going to start to interact with the Milky Way. And then things are going to happen very, very quickly. So about, 100 million years after that, stars and gas, basically stars are going to be scattered all over the place. Gas clouds are going to start colliding, forming new stars. The night sky is going to light up. It's going to look vastly, vastly different than what we see now. It's going to look a lot more chaotic. And then 3.9 billion years, it's going to look even more chaotic. You're going to see a lot of star formation. You're going to see a lot of gas clouds, things like that. But then things are going to kind of settle down. And then at about 7 billion years, when things finally settle, we're no longer going to see this hazy band in the sky anymore. We're actually going to see essentially an even distribution of stars in the sky. So we're no longer going to be living in a disk galaxy. We're now going to be living in that spherical galaxy. We're going to be living in an elliptical galaxy. And that's essentially going to be the fate of the Milky Way, is that it's no longer going to be a spiral galaxy. It's going to be an elliptical galaxy. And that's essentially the stars are just going to burn out, and then we're just going to be left in a cold, dead galaxy. And that's essentially that's the end of the talk. Sorry to leave it on such a bummer, but yeah. So that's essentially the origin and the fate of the Milky Way.
Are you observing other galaxies doing that?
Yes, you can actually see. Well, you can't watch. Obviously, you can't watch this happen in real time. Obviously,
Different stages, right?
say again. Sorry.
You see different stages of that occurrence, right?
Yeah, absolutely. Yeah. So you can see like the precursors to it. Galaxies, in the thick of it. Galaxies, just exiting that stage. You can see every stage of that process happen in different snapshots throughout the universe. Yeah, you can definitely find that. You just can't watch that process happen in real time, though. You just get the snapshots of other objects.
Are there any other questions?
Yes, I do have one. You mentioned Hubble, and that's been on my mind. One of the biggest things, but not Hubble, but the Webb is deeper and farther images. And are they going to use it to study our galaxy more?
Yeah, well,
Something.
yeah, I think the major, for sure they're going to do a lot. They're going to do as much as they can with James Webb, but I think the two main missions are identifying the origins of galaxies and identifying, essentially identifying the origins of solar systems. And that, they're trying to find like extrasolar planets and trying to understand how solar systems form. And so that can only be done within our own galaxy. But as to, like the structure of the galaxy and trying to look through the dust and see things, as far as we can on the other side of the galaxy, things like that. I'm not sure that's the first priority of James Webb, but, obviously there are astronomers proposing to use James Webb, and I'm sure everybody's going to use it to the greatest extent they can to do anything they can with it, anything feasible. Yeah.
Another thing for you. Did you hear that where NASA is getting with SpaceX to maybe look at doing a resurface on the Hubble?
Oh, I did not know that.
Did you hear that?
No, I didn't hear that. That's interesting.
It hit the news yesterday.
Is that supposed to be manned, like a crewed?
Yes.
Oh, interesting.
Yes. And
Oh.
we put newer, updated equipment, because I know the ideal originally was for both of them to work together.
Mm-hmm.
And Hubble has done so much. I would hate to see it be wasted.
Yeah, for sure. Yeah, yeah, I do remember. I do remember years ago when one of the gyroscopes failed, that Congress had to basically approve money to send somebody up to actually put the new gyroscopes in there so that way it could actually point again. But then they said, that's it, we're not spending any more money on it. So yeah, so that I don't know if SpaceX is gonna send a manned mission up there to actually service it, I think it'd be fantastic.
They're in the talks about it, so
Yeah.
let's hope it goes through. But thank you. I enjoyed your talk.
Oh, thank you.
A question. So in, I think it was 1980s, the COBE probe, was it? COBE, the Cosmic
Mhm.
Background Explorer.
Mhm.
I think that established that a Big Bang didn't happen in a central location, yeah?
Right, yeah.
Did the theory of galaxy formation change after that was established?
No, well, no, because Kobe, well, to be honest, Kobe didn't identify that there was no central location of the Big Bang, because I mean, really the issue is that the way we think the Big Bang happened is that it's essentially it's the expansion of space from a single point. So no matter where you are in space, you're moving away from everything else. So there is no central location. There should be no central location. It's essentially like being on the surface of a balloon, right? Like there's no central part on the surface of a balloon. There's no, like, basically if you're inflating a balloon and you're only stuck on the surface, there is no center, right? It's all the same everywhere you are on the surface of a balloon.
So
Right.
it wasn't the
There's no
purpose of
there's no
COBE to
preferred
find a,
location.
so it wasn't, I may be mistaken, wasn't the purpose of COBE to look for a hotspot?
Well, it is looking for hotspots. So one of the things they did, so what they wanted to do was they wanted to look for basically they wanted to look for anisotropies in the background radiation. What that means is they wanted to look for hotter and cooler regions in the background radiation, because we knew before that we knew that the background radiation was essentially uniformly 3 degrees Kelvin everywhere, every direction you looked. But what they wanted to do was measure the temperature differences to like a millionth of a degree to see temperature fluctuations in the background. And if they could find that, then that indicates that, you know, the universe didn't start out perfectly smooth, which it shouldn't, because if it did, then we wouldn't be here. And so there should be tiny fluctuations in the temperature of the background. And those temperature fluctuations, you know, it's like the butterfly effect, right? Those temperature fluctuations lead to galaxies, essentially, right? So, so where things are cooler, things can condense, like particles can condense and form galaxies and so on, and then we end up here, right? But if it was uniform, if the temperature was uniform throughout, then there should be no reason for anything to condense, right? There should be no reason for anything to be attracted to anything else, right? So like if you have, like if you existed in, if in space there were only 4 marbles, right, and they were equidistant apart, they would never be attracted to each other. They would just sit there, right? But if you move one in slightly closer to the others, then all of a sudden they're going to be attracted by gravity and move together, right? And so that's what they were looking for, was the differences in temperature.
Sorry, thank you.
Yeah, thank you.
There any more questions? Okay, if I can get out, when we drop off the live, if I can get everybody on the Zoom to please stay on for just a couple of minutes so we can get a couple of things done. So please don't dash away for a few minutes yet. I won't keep you too long. Well, Patrick, thank you very much for your presentation. So
Yes.
lots of great information, and I think everybody enjoyed it. So again,
Right.
Thank you very much.
Yeah, thanks for having me.
For those of you watching on the recording, we're going to stop the recording now while we do, and then we'll do some club business. But thanks for everybody who's watching us in time delay mode. So go ahead and
Have a good night, everybody.